In the previous chapter, we have been discussing the effects of the forces acting on a body through their lines of action or at the point of their intersection. But in this moment chapter, we will discuss the effects of the forces at some other point away from the point of intersection or their line of action. The present topic is the moment. So, moment is basically a turning effect and it is produced by a force on the body on which it acts. The moment of a force is equal to the product of the force and the perpendicular distance of the point about which the moment is required and the line of the action of the forces. Mathematically, moment M equal to P cross L, where P the force acting on the body and L is the perpendicular distance between the point of application of the force and the point about which the moment is desired. The moment is represented in Newton meter, kilonewton meter, Newton millimeter, kgA meter, etc. in units. If we take the graphical representation of moment, consider a force P. It is represented in magnitude and direction by the line say P and the line AB. Let O be the point O about which the moment is required to be found out. Now from O, draw a perpendicular line over AB. Now join AO and BO. If you take a clear picture, that will be like this, that is AB, that is O, dotted line, that is C, this is the force P. Now moment of force P about O equal to P into OC, and P is represented by side AB of the triangle formed. So moment equal to AB into AC, but AB into AC is equal to twice the area of the triangle. If you modify the form of AB into AC like in this way, that is 2 into half into AB into OC, where half into AB into OC is equal to the area of the triangle AOB. So we can say that moment equal to 2 into area of the triangle. Thus, moment of a force about any point is geometrically equal to twice the area of the triangle, whose base is the line representing the force and whose vertex is the point about which the moment is required to be found out. Now, the types of moment. The moments are basically two types. One is the clockwise moment and another one is the anti-clockwise moment. The general convention is to take clockwise moment as the positive and anti-clockwise moment as negative. The clockwise moment of a force is It is a moment of force whose effect is to turn or rotate the body in the same direction in which the hands of clock moves. And in anticlockwise moment, it is the moment of a force whose effect is to turn or rotate the body in the opposite direction in which the hands of a clock move. Now, Varignon's principle of a moments or law of moments. It states that if a number of coplanar forces are acting simultaneously on a particle, the algebraic sum of the moments of all the forces about any point is equal to the moment of their resultant force about the same point. Let us consider, for the sake of simplicity, two concurrent forces P and Q represented in magnitude and direction by AB and AC. Say this is AB, this is AC, and the force P along AB, force Q along AC. Let O be the point, let O be the point about which the moments are taken. Through O, draw a line OD parallel to the direction of force P. That is OD. To meet the line of action of force Q at C. Now, with AB and AC as two adjacent sides, complete the parallelogram AB DC. So now AB DC is a parallelogram. Join the diagonal AD of the parallelogram and OA and OB. Now join AD, that is the diagonal of the parallelogram ABDC. Next, join the line AO and OB. From the parallelogram law of forces, we have already studied or discussed the parallelogram law of forces in our previous lecture, and the link of the previous lecture is available in the description box of this tutorial. So, from the parallelogram law of forces, we know that the diagonal AD represent in magnitude and direction the resultant of the two forces P and Q. The moment of the force P about O equal to the moment of force P about O is equal to twice the area of triangle AOB. How it comes? From the graphical representation of moment, which already discussed in the few minutes later. the moment of force P moment of P about O equal to twice the area of triangle AOB, which already discussed in this lecture. So from the graphical representation of moment we can conclude this one. Similarly, the moment of force Q about O equal to twice the area of triangle AOC and moment of resultant force R about O equal to twice the area of triangle AOD, triangle AOD. But from geometry of the figure, geometry we find that area of triangle AOD equal to area of triangle AOC plus area of triangle ACD. That is equal to but area of triangle ACD equal to area of triangle ADB that is equal to area of triangle AOB. As two triangles AOB and ADB are on same base and between same parallel line. So area of triangle ADB will be equal to the area of triangle AOB. Hence area of triangle AOD equal to area of triangle AOC plus area of triangle AOB. Now multiplying both sides by 2, into area of triangle AOD equal to 2 into area of triangle AOC plus 2 into area of triangle AOB. Now, from the concept of graphical representation of moment, we may conclude that moment of force are about point O equal to moment of force P about O plus moment of force Q about O. We have considered here, for the sake of simplicity, only the two forces P and Q, but this principle may extended for any number of forces. Now we will take a problem. A force of 15 Newton is applied perpendicular to the edge of a door 0.8 meter wide as shown. Now find moment of that force about the hinge of the door. This is one question, and as a part of this question, it is again said that if this force is applied at an angle 60 degree, if this force is applied at an angle 60 degree to the edge, of the same door, then find the moment moment about the hinge. Sorry, there is repetition of, sorry, about the hinge. The diagram is, in first case, so this is the door, 15 Newton force is being applied here, and the distance between the hinge and the point of application or of the force or the edge of the door is 0.8 meter. This is one figure, and in the second question the figure will be like this. This is 0.8 meter, and the force will act in this direction. This is 15 Newton. The magnitude is same, but the direction of the force is different. Here the force will act inclinedly at an angle 60 degree with the horizontal. So in the two cases we have to find the moment of force 15 Newton about the point O, that is at a distance 0.8 meter from the point of application. Now moment when force acts perpendicular to the door. In first case we calculate moment when the force acts perpendicular. Here moment M equal to P into L. P, value of P is 15, L is 0.8, so it will be 12 Newton meter. So this is one answer. And moment, calculation of moment, my pen is not working properly, so there's some problem. Moment when force acts inclinedly at an angle 60 degree with the door or with the horizontal. this part of the example may be solved either by finding out the perpendicular distance between the hinge and the line of action of the force, or by finding out the vertical component of the force. So there is two ways. We will discuss both the way here. In first case, that is the 60°, it will be 30°, 30° angle. So this is C, point C, and this is 0.8 meter. So from the geometry, OC equal to OB sine 60°. OC equal to OB sine 60°. That is equal to 0.8 into 866, that is 0.693 meter. So moment will be 15 into 0.693, that is equal to 10.4 Newton meter. In second case, it is 15 Newton So the component of this force will be in vertical direction, it is 15 sine 60, and in horizontal direction it will be 15 cos 60. Distance is 0.8 meter. So in the second case, we know that the vertical component of the force equal to 15 sine 60°, 15 into 66, so 13 Newton. that is equal to 30 Newton. So moment equal to 13 into 0.8, that is 10.4 Newton meter. So this is the answer. In both the cases the answer is same, so there is no question. Since the distance between the horizontal component of the force P cos 60 degree and the hinge is 0, therefore the moment of horizontal component of the force about the hinge is also 0. Obviously they are both are in the same level, so basically there is no distance, so there is no question about hinge in respect of the horizontal component of the force. Now the application of moments. Though the moments have a number of applications in the field of engineering mechanics, yet the following are important from the subject point of view. The number one is the position of a resultant force, and second one is the lever. Position of resultant force by moments. It is also known as the analytical method for the resultant force. The position of a resultant force may be found out by moments as discussed below. First of all, find out the magnitude and direction of the resultant force by method of resolution. In second step, equate the moment of the resultant force with the algebraic sum of the moments of the given system of forces about any point. This may also be found out by equating the sum of clockwise moments and that of the anticlockwise moments about the point through which the resultant force will pass. Now, for better understanding, we will take one example. The question is, four forces equal to P, 2P, 3 and 4P are respectively acting along the four sides of a square. Say this is one square, A, B, C and D. The four forces are along AB it is P, along BC it is 2P, along CD it is 3P, along DA it is 4P. So the four forces P, 2P, 3P and 4P respectively acting along the four sides of a square ABCD taken in order. Now find out the magnitude and direction and position of the resultant force. So the main question is the resultant force, its magnitude, direction and position. Now resolving all the forces horizontally, we may get P minus, sorry, this is 3P, this one and this one in horizontal direction. So summation of horizontal forces will come minus 2P. Similarly, summation of vertical forces, it will be 2P minus 4P, that is also minus 2P. Now we know that R will be summation of root over horizontal force are equal to root over summation of horizontal forces square plus summation of vertical forces square. That will give you, so minus 2p square plus minus 2p square, so that is 2 root 2 p. So the magnitude of the resultant force are equal to 2 root 2 p. Now the direction tan theta equal to, we know, summation of v by summation h. So this one will be, that is 1. So theta equal to 45 degree. Theta is the angle which the resultant force makes with the horizontal. Since summation h and summation v are both are negative, so theta lies between 180 degree and 270 degree. So actual value of theta, equal to 180 degree plus 45 degree, 225 degree. So the direction of resultant now 225 degree. Now the next part is the position of the resultant force. Let x equal to perpendicular distance x equal to perpendicular distance between A and the line of action of resultant force. The line of action of resultant force, and A is the side of square ABCD. Now equating the moment about A and equating the same. So before that we need to draw the position and of the resultant diagram. So this is the square for P, that is A, that is B, C, that is D. Now this one is small a, the side of the square. Suppose this one the resultant R, this angle is 225 degree. The perpendicular distance, this one is the, say, x. The position of the resultant overextended BA at a distance small h. Please note this figure in your notebook. Because of shortage of space, I need to erase this one. Now, taking moment about A and equating the same means taking moment of the resultant force about A, and similarly equating that one as per our step 2, which we already discussed, that the moment of the resultant force uh, will equate with the algebraic sum of the moments of the forces of whose the resultants are calculated. So as per the step 2, the equation will be 2 root 2 p x equal to 2p into a plus 3p into a. That will give you, after simplification, x equal to 5 x equal to 5a by 2 root 2. So the perpendicular distance between the resultant force and the point A is 5a by 2 root 2. Now if you want to find the value of h, then in the similar way you have to take moment of the forces about A and equating the same. So in that case, p into 0 plus 2p into h plus a plus 3p into a equal to 4p into h. So after simplification, it will 2h equal to 5a. So h equal to 2.5a. So this is the answer. Our next topic is the lever. Lever is a rigid bar, straight or it may curved also, and is hinged at one end. It is free to rotate about the hinge called fulcrum. The common example of the use of lever are crowbar, pair of scissors, fire tongs, pliers, etc. It may be noted that there is a point for effort called effort arm and another point for overcoming resistance or lifting load called load arm. So lever are basically are of two types. First one is the simple lever and second one is the compound lever. Simple lever is further divided in three orders: first order lever, second order lever and third order lever. Here two figures are shown. In both the cases, a load P applied on the effort arm, W weight lifted on the load arm, small a is the length of the effort arm and small b is the length of the load arm, and here F is the hinge point, that is the fulcrum. Now taking moments of the effort and load about the fulcrum and equating the same, then the equation will be P dot A equal to W dot B. So W by P equal to A by B. The terms W by P and A by B are commonly known as mechanical advantage and leverage of the lever. A little consideration will show that in order to increase the mechanical advantage, either the length of the lever arm A is to be increased or length of the load arm small b is to be reduced. The simple levers which already told that the are of three orders. First order, in this type of lever, the effort and load act on the opposite sides of the fulcrum. In second order lever, the effort and load act on the same side of the fulcrum, but effort acting at a greater distance than the load, or in other words, load is acting between the fulcrum and the effort. In third order lever, the effort and load act on the same side of the fulcrum, but load acting at a greater distance than the effort, or in other words, effort is acting between the fulcrum and the load.